We present PointALCR, the adversarial latent GAN and contrastive regularization for point cloud completion. Raw points directly captured by 3D scanning devices are usually sparse and incomplete due to the limited sensor resolution and occlusions. Hence, it is essential to infer the complete shape from the partial observation so as to facilitate various downstream tasks such as classification and shape manipulation as required in real-world applications. Recent learning-based methods are all generative approach and can be grouped into two main categories. One is based on autoencoder and the other one is based on GAN. However, the generative ability of the combination of these two frameworks still remains unclear. We follow the GAN-based SODA framework called the PFNet. It introduced a multi-resolution encoder and a point pyramid decoder as generator for shape completion. PFNet shows the most realistic completion results compared with high-quality 3D dataset. Other than generative methods, contrastive learning is another popular approach adopted in self-supervised learning. Contrastive learning acts on pulling the anchor close to positive instance and push the anchor far away from negative instance in the feature space. Previous work applied contrastive learning mainly in 2D high-level vision tasks, and few have been reported in 3D vision tasks. In our work, we seek to combine GAN, autoencoder, and a new contrastive regularization in order to design a powerful generative framework for point cloud completion. The objective is to complete the missing region for given incomplete point cloud with high quality. The input is an incomplete point set with endpoints, and the network generates a complete point set with R endpoints, where R is the upsampling scalar. Traditional GAN-based point cloud completion methods consist of a generator networks that maps incomplete point cloud P to target point cloud space X, and a discriminator networks that map X to R. The generator aims at learning generated distributions as similar as ground truth distributions. The discriminator is used to distinguish the data produced by the generator from the real distribution. From previous approaches, we observed that the intermediate latent feature possessed the prior information of data distribution, which ideally enhanced the representative and generative ability of GAN. So, in order to use latent point distribution feature, we separate both the generator and discriminator into two networks, which is highlighted by the red rectangle. We assume that F1 and F2 are the latent point feature map, and the latent space between G and F1 equals to that between D and F2. The latent point feature map is a deterministic map since it represents the disentanglement of input and target point cloud data. There are two constraints in the latent GAN procedure. The first constraint is to align the reconstructed distribution to real data distribution, and the second constraint is to ensure that the distribution of the output of F2 be the same as the distribution at the input of G. Since optimizing the min-max equation leads to distribution PGX equal to PDataX, it is obvious that the second constraint stands. Hence, the F1 and F2 could be performed as one same latent autoencoder network. In this way, the training procedure of the PointALCR can be described using the single min-max equation mentioned above. By concatenating the latent feature, it can help generator G to generate complete point cloud similar enough as target distribution X, and make discriminator D distinguish reconstructed shape from G more accurately. The input of AL-GAN is a point set of size n. AL-GAN first downsamples the input into different resolutions by farthest point sampling, or so-called FPS, and obtains the other two feature point sets. All three point sets are propagated into combined multi-layer perception, or CMLP, separately in a similar way as in PFNet. In CMLP, each layer of PointNet MLP is max-pooled into multiple dimensional feature space and concatenated into a latent feature vector F. Thus, F contains the hierarchical feature of all three point sets. The generator takes the latent feature vector F as input and output a complete point cloud of size 3n. Since the latent feature F contains features from different scales, The hierarchical FPN structure is adopted by the generator. We assign 3 feature layers passing F through fully connected layers. Each feature layer predicts a point set with different point numbers. We then assign ground truth point sets into 3 resolutions to calculate the chamfer distance for the output of each layer. Finally, we concatenate 3 predicted point sets into one final set with 3 endpoints as the final complete set. For the discriminator, it takes the final complete set and then concatenates the latent feature vector f as input. Then, put the combined feature into a PointNet MLP with several linear layers to distinguish the distribution to target point cloud. The total loss function is combined with contrastive regularization, completion loss, and adversarial loss. The contrastive regularization targets to pull positive pairs closer and push the negative pairs far away in the feature space. In this paper, the positive pairs are the generated results R and ground truth J, and the negative pairs are the incomplete input I and its corresponding reconstructed results R. As for the feature space, we use per point feature denoted by feat I, which is extracted by pre-trained model from PointNet++. The completion loss is the chamfer distance between the generated point cloud R and ground truth J. All 3 point sets produced by generator are taken into account. The adversarial loss in PointALCR is similar to that in GAN, where R is the reconstructed results, D is the discriminator, and G is the generator. We compare our method against several representative methods on point cloud completion. All methods engaged are trained in an unsupervised manner, that is, without label information. To evaluate the above methods, we use 3 metrics, including chamfer distance, prediction to ground truth error, and ground truth to prediction error. The error of overall complete point cloud contains the prediction error of the missing region and the change of the original partial shape. The results of Table 1 show that our method outperforms other methods in most categories on both errors. Table 2 shows that our method outperforms in 6 out of 8 categories of objects compared to other methods. We obtain 8.2% relative improvement compared to the second best method. The results in Table 1 and 2 indicate that PointALCR can generate more high-quality point cloud with less distortions in overall point cloud and achieve better performance with finer global and local structure completion. We visualize the output point cloud generated by the several previous methods. All objects come from the test set. Compared with other methods, the results of PointALCR present higher level of restoration and less genus-wise distortions. We also visualize the zooming or reconstructed missing regions of point cloud. We can see that our reconstructed shapes are very similar with their corresponding ground truth. To prove the effectiveness of AL-GAN module, we conduct ablation study on classification tasks on ModelNet 40 and a small-scale point cloud completion task on chair and table objects in ShapeNet Core. To demonstrate the feature representative ability of AL-GAN, we train PointNet and PointNet++ with AL-GAN on ModelNet 40 and evaluate their overall classification accuracy on a test set. The results in Table 3 suggest that with AL-GAN, PointNet and PointNet++ have higher test accuracy compared to that without AL-GAN, which indicate that AL-GAN has a better feature learning ability. In order to evaluate that AL-GAN and contrastive regularization in GAN-based network, we further compare the generative ability of our PointALCR without AL-GAN or contrastive regularization. We select chair and table of object in ShapeNet Core and train PointALCR without GAN to see the difference between its completion results with ground truth point cloud. In Table 4 and 5, we compare the chamfer distance, prediction to ground truth error, and ground truth to prediction error between with and without AL-GAN or CR. The results show that on all 3 metrics, the network with AL-GAN or CR are better than those without. This indicates that with the enhancement of latent feature extracted by AL-GAN and contrastive regularization, the generative ability of GAN-based point cloud completion network could be improved. Our contribution can be summarized as below. We designed PointALCR that combines the generative ability of GAN and autoencoder to reconstruct the incomplete point cloud with higher quality. We proposed a new module named Adversarial Latent GAN or ALGAN to extract point distribution feature and enhance the generative ability of network. We introduced a new constructive regularization loss to enhance the discriminative ability for point cloud completion. And finally, we showed that PointALCR achieves superior performance to existing methods on several challenging point cloud completion tasks. Thank you for your attention.